So the last topic we're going to talk about is in section 1.5. We're going to revisit partitions of sets. So we're going to start by recalling some facts that you may remember from discrete math. So we'll say that a collection, which I'll go with S, this curly S, of subsets of a set A are called pairwise disjoint if and only if every two distinct subsets that belong to S are disjoint. So to be disjoint, it means that the intersection would be the empty set. So let's look at an example. Let's say my set B is going to be the set 1, 6. C would be the set 2, 5. And D would be the set 4, 7. If I take any two of these and compute the intersection, so if I take B intersects C, B and C don't have anything in common, so the intersection would be the empty set. If I take B and D, intersect them, they don't have any elements in common, and the same thing for C intersect D. So then I can say that the collection S of the sets B, C, and D is pairwise disjoint. Okay. So if I take any pair of sets in this collection and take the intersection needs to be the empty set if they're pairwise disjoint. Okay, so now that we know what pairwise disjoint is, we can talk about a partition. A partition of a set A is a collection of non-empty subsets of A so that every element of A belongs to exactly one subset in S. So there's really like three conditions for a partition. I'll just write them out here. The first one is that this partition, none of those sets can be the empty set. For all X in my collection, so my collection of subsets cannot contain the empty set. The second condition is that for every pair of sets in this collection, X and Y and S, either they're identical sets or the intersection is empty. And the third condition is that if I take the union of these sets, I would get back the set A. So let's look at an example here. An example let's say my set A is the set of numbers 1, 2, 3 up to 6. And so one partition of A is the set of sets 1, 3, 6, the set containing 2 and 4, and the set containing 5. None of these, the reason why this is a partition, so none of these sets are the empty set. So condition 1 holds. If I take any two of these and compute the intersection, intersected with 2, 4, the intersection would be the empty set, and the same thing for the other two pairs. So 1, 3, 6 intersected with 5 would be the empty set, and 2, 4 intersected with 5 would be the empty set. So condition 2 holds. And then finally, if I take the union of all these sets together, I get back my set A. So this would be a partition. So I'll say, but this collection, so the collection 1, 4, 3, 5, and 2 is not a partition of A. And why is it not a partition of A? Because remember, A contains the element 6, and 6 is not in any one of these 3 sets. And every element of A needs to be in one of these sets. So I kind of want to give you a picture idea of what is going on when you have a partition. So for example, let's take this partition that we had here of the numbers 1 through 6. So remember when we were doing Venn diagrams, we represented a set with a circle. So let's say this is my set A, has the numbers 1, 2, 3, 4, 5, and 6 in them. And what you're doing is you're breaking this set up into pieces. So you're breaking the circle up into pieces. So my circle, so you're putting the elements 1, 3, and 6 together, the element 2 and 4 together, and the element 5. So that would be a partition. You're breaking up your set into these subsets.